We're going to continue on here. Last time we got into, I think, chapter 9, and we talked a lot about intermolecular forces. And remember that pretty much intermolecular forces are the forces that hold basically one molecule together with another. And this could be two molecules that are basically the same, how something kind of holds together with itself. Also, it is how other molecules, different molecules, for example, interact with one another. All the basic intermolecular forces have a basic sort of interaction as to how they work. There's basically a positive side and a negative side to each of the molecules involved in an intermolecular force. And it really is that electrostatic attraction. So that is the opposite attraction. So really the negative side of one molecule is attracted to the positive side of the other molecule. And that's essentially what holds them together. That is different than we also touched upon intramolecular forces a little bit. Intramolecular forces are the forces within a molecule that holds it together. Like, for example, the electrostatic attraction we see in ionic compounds between the ions, also covalent bonding, where we have sharing of electrons. So, for example, as we looked at, I think if you took like one water molecule by itself, intramolecular force would be the force that holds the oxygen hydrogen together on one side and the oxygen hydrogen together, the sharing of electrons there on the other side within that one individual water molecule. So these are always stronger than these guys here. But we mainly focus, though, on intermolecular forces. And there's kind of basically three sort of types. There is hydrogen bonding, which is a very strong intermolecular force. And that is a bond between hydrogen and an electronegative element like nitrogen, oxygen, or fluorine. So again, in order to have the ability to do hydrogen bonding, that hydrogen does need to be directly attached to a nitrogen, oxygen, or fluorine. That's going to create a really polar sort of bond there, and that's going to give it that kind of positive, negative side that it's going to need to sort of interact with intermolecular forces. This is pretty much your strongest intermolecular force that you're going to come across. It is technically a form of the other type of intermolecular force, which is a dipole-dipole interaction. And dipoles, as we talked about, is molecules, for example, that are polar, and they have a dipole moment. And part of having a dipole moment and being polar is that they always have a positive side and a negative side due to the unequal sharing of electrons. And again, it's going to give it that ability to do so. So these two here are really the forces that we see used with polar molecules. Obviously, if the molecule has the ability to hydrogen bond, it's going to choose hydrogen bonding as sort of its choice. If it is a polar molecule, but really doesn't have a hydrogen to hydrogen bond with, it will use dipole-dipole interaction to help it on. We also saw with that ion dipole interaction, which is sort of what happens when we dissolve an ionic compound in something like water, which is polar. Again, like all the ions get surrounded by, say, the negative side of water, while the positive guys, the negative ions get surrounded by the positive side of water and stuff like that. Kind of the weakest of all the forces that we talked about was dispersion forces. And dispersion forces are the weakest. And they are pretty much your nonpolar molecules sort of route of interaction. And the reason they're really weak is they do, for the most part, have to rely upon something happening in order for them to have the ability to interact. So because they're technically a nonpolar molecule, as we've talked about before, there's going to be equal sharing of electrons in the molecule as a whole, which means it's kind of like a neutral molecule, which means when you have two of those guys, for example, together, there is no sort of ability to interact with one another right out of the box because they pretty much don't have any charges. They don't have a negative side or a positive side. So one way that it can sort of occur is what's known as an instantaneous dipole. And an instantaneous dipole, the electrons, for example, in one of the molecules, maybe all sort of end up on one side of the molecule versus the other. That, as we talked about, will temporarily create a separation of charge on that normally nonpolar molecule. And if it is next to another one, it would also cause the electrons in that guy to kind of go the opposite way of the negative. And now these two guys that normally do not sort of carry this sort of separation of charge will now have a temporary sort of separation of charge and a way to sort of interact with one another. This is why, again, it's relatively weak and temporary because it requires this to sort of happen. And again, as soon as those electrons sort of shift one way or the other, it's going to kind of break apart, make new sort of interactions. And it's nothing that's going to be pretty much fixed in place. And that's very different than what we see with dipole-dipole interaction. These guys, because they have a dipole moment, because they are polar, no matter what you do to them, they always have a positive side and negative side, which means right out of the box, they're pretty much good to go to interact with other molecules because they have that positive and negative side. Something like dispersion forces does rely upon something happening, either an instantaneous dipole. You could also induce a dipole by temporarily putting a ion near something that's nonpolar or a polar molecule near something that's nonpolar. It will cause that sort of separation of charge and an interaction to occur. Uh, the importance of intermolecular forces is really how molecules interact with themselves and other molecules. So in terms of how they interact with themselves, the stronger the intermolecular force, the higher things like boiling point and melting point, freezing point, we would expect it to have because it's going to hold itself together really strong. And it's going to take a lot of energy to get things away from each other. For example, going from liquid to gas, and like when you go at the boiling point, it'll take a lot more energy for those guys to escape each other because they're held together by really, really strong intermolecular forces. If you have something that is held together by, say, dispersion forces, which is a relatively weak intermolecular force, those guys are going to have very low melting points and boiling points because if you just kind of sneeze at them, it doesn't take a lot of energy for them to kind of break apart because they're really, really weak, and it will go into the gas phase relatively easier. That's also why, again, a lot of organic compounds, which are nonpolar, use dispersion forces as their main route, and also why, again, a lot of them are very volatile because they can very easily kind of break apart from each other because they're not held together very, very tightly. So it takes not a lot of energy to do so. As we'll also see in the next chapter as well, these intermolecular forces are really important in how different molecules interact with each other, things like solubility, whether things will mix together or not mix together, depending on sort of the intermolecular forces that they're using. Now, everybody pretty much can use dispersion forces, and that's why over the short period of time, there can be some interaction that could happen. Like we talked about sort of oil, vinegar, over a short period of time, they'll kind of mix, but over a long period of time, they can't maintain that sort of interaction that occurs. Also with dispersion forces, we talked about the idea that the longer, or not really longer, I guess, larger the molecule is, the higher the molar mass, the stronger the dispersion force will be because more molar mass, more atoms, more electrons, more chances for interactions to occur, and electrons to sort of be dissociated and polarized one way or the other. Any questions on any of that stuff we talked about there? All right, then let's get into a little bit more about some of the liquid state. Liquid molecules are close together, obviously closer than in the gas state. One of the sort of hallmarks of the liquid state is their kind of closeness, but they still have enough energy to sort of pass one another and move around one another. And again, that's why we do think of liquids obviously as being fluid in that sense. Again, when we lock into the solid state, they sort of lose that energy and ability to move around. Viscosity is the resistance of a liquid to flow. It is related to intermolecular forces, and the water has a low viscosity. Motor oil, for example, has a high one. You can also decrease the viscosity with increasing temperature. Again, that adds more energy, so it's going to give everybody a little bit more movement to be more fluid, right, and flow a little bit easier. Now, when we talk about water, there's a couple of important sort of forces that really do relate to how things interact. For example, cohesive forces. Cohesive forces are the forces between molecules in a single substance. Uh, so basically, that's the idea of how a molecule interacts with itself. Hydrogen bonding, for example, in water is an example of a cohesive forces. When all the water molecules get together, again, they're going to hydrogen bond between the negative oxygen side and the positive hydrogen side. And again, that is the force that holds it together. Adhesive forces are the forces of attraction between two different molecules. And as we will see in a second, these are really the forces that account for why, for example, we see like a meniscus when we look at a liquid in a glass container where it kind of does that curvature. And in that case, the adhesive forces are actually stronger than the cohesive forces. So we get that stronger attraction to a different sort of molecule. Surface tension is that elasticity that's found on the surface of a liquid is energy needed to expand the liquid surface. It's higher for liquids with greater intermolecular forces. For example, you could, kind of lay a paperclip on some water, or certain bugs, right, can kind of walk over water, right, and not sort of break through. Surface tension is greater in water because of that hydrogen bonding, which is a really strong interaction. So what happens, for example, when we think of water molecules, say at the surface, as we will see there in just a second, instead of water molecules, say at underneath the surface of the liquid. At the surface of the liquid, we have interactions between water molecules sort of to the sides and down. And what that does is, as they're interacting to the sides and down, it sort of spreads out the surface of the liquid. There's no sort of interactions going upwards. So you have this unequal sort of pulling sideways and down, and it's going to make that surface a lot tighter, as opposed to, say, a water molecule here in the center. It's going to feel sort of attractive forces all around, and it's not going to kind of pull itself out and make it like you see at the surface. Um, and that's what we see here again. These guys at the surfaces feel these attractive forces heading this way, this way, and this way, going to create a really tight sort of surface tension there at the very top. When we look at somebody well beneath the surface of the liquid, it's going to feel, I won't say perfectly equally, but it'll feel basically interactions and attractions all around it. So it's not going to get kind of like pulled in a sense in one direction or the next. Now, one of the ways that you could kind of break, for example, the surface tension, um, is to add something like soap. Soap or detergent uh, to the surface tension is greatly reduced, for example, in water. If you look at soap, soap, for example, looks something like this, and it's really and these are all basically carbons and hydrogens basically attached all the way across line structure and organic here, but I won't draw it off. But basically, they're carbons and hydrogens. And there's really kind of two parts of soap. And the two parts of soap is the back end here. And this back end is what is sometimes referred to as the nonpolar tail of soap. And that's because it's basically all carbons and hydrogens, a really long chain of carbons and hydrogens. Up here, this is actually the polar head, is sometimes referred to, of soap. And what that allows soap, for example, to do is when you are dirty and want to wash your hands or whatever it may be, most of the time dirt is nonpolar. So when you put soap on, for example, it is that nonpolar part of soap that will basically surround the dirt. in what is sometimes referred to as a micelle, as it kind of surrounds the dirt. And that's going to work really well because, again, the dirt is nonpolar. That part of soap is nonpolar, so they're going to interact really well. They're both going to do like dispersion forces and interact really well. What that essentially will do is all soap molecules will surround the dirt, and what its soap molecules will typically do at that point is line up the polar part on the outside. And that's really good because typically when you use soap, you usually wash it off with something like water, which is polar, right? So when you go to wash it off with water, it will actually interact with the polar side of soap, which has the dirt trapped inside, and off goes the soap molecule that has the dirt trapped, and you're clean at that point. So soap's an interesting molecule like that. And what happens though when you put soap on, if you think about, for example, if you have a strong surface tension, it prevents on a non-polar surface like an umbrella or a wax car. If you ever put water on like your car and it has a lot of wax on it or something like that, there's been wax, you typically will see the water bead rather than spread out, right? You'll see all that beading that basically is happening. Again, that's sort of the water and the non-polar wax surface interaction with each other. When you go to wash your car, right, you wet it down and then you typically will soap it up, right? And it's at that point, what the soap will do is it'll get in between the water molecules surface tension and allow it to actually spread out. And you can kind of see that when you take like the sponge and start doing it, kind of see the water sort of spread out with all the soap in it. And that's because that polar side of the soap is able to get in between the surface water tension and basically kind of separate out those molecules. And that's what allows the water to sort of spread out at that point. Again, that's going to interact okay because there's polar and polar sort of part of that interaction that's happening there. So adhesive and cohesive forces, again, are really important for other things like we talked about. It is really why we do see uh, like a meniscus, and that's through, for example, sort of capillary action. If you have a small diameter and it will sort of suck up a liquid due to that. And if you have really strong adhesive forces, what we see here, for example, like water in a glass container, the attractive forces between water and the glass container is actually stronger than the attractive forces between water and itself. So what happens is when the water is basically at the edges of that glass container, it will basically start to rise up the sides of the wall due to capillary action, that attractive forces. And that is what gives us our curvature of the liquid or our meniscus. This is also why we talked about that, in a sense, we always, in this type of meniscus, read from the bottom of the meniscus, because without that interaction on the walls of the container, basically the volume would be down at the bottom there, and that's where the true volume is. That's why we always kind of read from the bottom meniscus to sort of counteract the capillary action because of the attractive forces that's happening on the walls of the container. As I might have mentioned before, not all sort of substances, for example, will create sort of a U meniscus. And mercury is an example of that. Mercury, the attractive forces between mercury and itself is actually greater than the attractive forces between mercury and the liquid and the glass container. So what happens is, instead of kind of curving upwards, the mercury kind of curves inward as the attractive forces between itself is stronger than the container, and we get this sort of opposite sort of meniscus in mercury. In this type of case, though, we would actually read from the top of that type of meniscus. And that, again, is because without that attractive force as an action, the actual volume is actually towards the top there, of the meniscus in that particular case. So in the cases here where we have adhesive forces greater than cohesive forces, we will see sort of that rising of the liquid, for example, through capillary action, giving us something like a meniscus. And if we have sort of cohesive forces that are stronger than adhesive forces, we can again get a sort of meniscus that heads in the opposite direction. Any questions on that? Now let's talk a little bit about vapor pressure, and we talked maybe a little bit about it in the previous chapter. But vapor pressure is the tendency of a liquid to basically evaporate. And the volatility of a liquid, if something is really volatile, it will go from the liquid phase into the gas phase relatively easy. And as we talked about, one of the things that are usually pretty volatile type liquids are things that use dispersion forces because they're very weak sort of intermolecular forces. In a large open container, it will evaporate completely because air diffuses most of the gas molecules um, and prevents them from re-entering the liquid. So really at any surface of a liquid, you have two things happening. You have evaporation, where guys are jumping out of the liquid phase into the gas phase. And believe it or not, you do have condensation, where the sort of gas molecules are dropping back into the liquid phase. So at the surface of any liquid, you basically have that whole thing sort of happening. Now, when we think about sort of if you have just like a little sort of drop of liquid or whatever it may be on, say, the desk or the bench or whatever it may happen there, it will eventually evaporate pretty easily in a sense by itself. And that's because you're going to have a lot of evaporation happening here at all points. You also will have air molecules that will push these molecules as they evaporate away, sort of away from your pile there. What that's going to prevent actually is the condensation part from happening. So as those molecules get pushed away, they're no longer there available to drop back into the liquid phase, and eventually your little kind of wet spot there will eventually evaporate. It gets much harder, right? If you throw that liquid into a container, right? It's going to take longer for that to happen because there's only a certain amount of molecules that are at the surface that can go and evaporate. And there's a lot underneath. So it's going to take a lot longer time for those guys to kind of work their way to the top and start basically evaporating off. Also gets even harder, right? If you put a liquid in there and you put a container or a stopper on it, right? Now there's no route of escaping, right? They can't get out. They can get out of the liquid phase, but because say your thing is stoppered, right? Those guys have nowhere to go, right? They can't fully escape. So a lot of them will condensate back and probably will not evaporate off. Now, as this process happens and we get these guys jumping from the liquid phase to the gas phase, what that's going to create right above the liquid are pretty much gas molecules floating around, right? And gas molecules, as we know, as they are moving around, will create pressure, and that is basically what is known as the vapor pressure of a liquid. It is the pressure associated with the gas molecules above the liquid portion of it. Liquids with high vapor pressure are said to be volatile. If they have a high vapor pressure, the only way to get a high pressure is you probably need perhaps a good amount of molecules kind of flying around, and that means that a lot of them have evaporated at that point and going to go into the gas phase relatively easier. The vapor pressure of a liquid is determined by the intermolecular forces. The larger the intermolecular force, the lower the vapor pressure. So the larger the intermolecular force, what that means is less molecules are going to make their way up, which means you will have a lower vapor pressure as a majority of them will stay in the liquid phase rather than going into the gas phase. And that's what we're talking about here. If we did put a stopper, for example, on this container, when we have a liquid in a closed container, if you look at sort of the initial sort of volume of that liquid at the very beginning, you're pretty much going to only have evaporation occurring. And in this case, as you evaporate, you are going to increase the vapor pressure over that liquid. But with the lid there, again, they have no escape route, which means you will then get some guys heading back in the opposite direction, going through condensation. At some point, it will reach equilibrium. And that's basically where the rate of evaporation will equal the rate of condensation. And at that point, what will happen is you oftentimes see perhaps the liquid level decrease a little bit because initially when you put the liquid in there is no evaporation, and then it starts pretty soon after the liquid gets in there. So at that point, you're going to evaporate some of those molecules from the liquid phase. They're not going to rejoin sort of the liquid because they're trapped. And eventually, what will happen is you'll see just a little bit of a decrease in the overall volume Again, because where these guys were here to start with, they're pretty much up here now to end with, and that means the liquid volume will come down a little bit. Now, there's one way that you could calculate sort of vapor pressure, and this was the Clausen-Clapeyron equation, and this is the natural log of the vapor pressure at the first temperature divided by the vapor pressure at the second temperature equals the delta H of vaporization. So the delta H of vaporization is the heat of vaporization, is sometimes referred to. And it is actually the energy required to go from a liquid to a gas, or backwards, the gas to the liquid, to remove that amount of energy. That's sometimes referred to as, remember, delta H is our enthalpy, our change in enthalpy. So it's the enthalpy of vaporization in this particular case. So what is the heat of vaporization? As I mentioned, it really is the energy required to do nothing more than actually change the state of a substance, either go from liquid to gas or gas for liquid. It will not change the temperature. So this occurs at the same temperature. This usually occurs at the normal boiling point of a substance, is where that happens. So for example, at 100 degrees Celsius, there's a certain amount of energy required, for example, for water to do nothing more than take water at 100 degrees Celsius in the liquid phase to 100 degrees Celsius water in the gas phase. So exactly at the same temperature, just to do that transition is the heat of vaporization. And roughly speaking, for water, it's roughly 2,260 joules per gram. So that is the amount of energy at the boiling point, if you had water, that you would need to put in there to not raise the temperature or lower the temperature, but to simply just take it at its boiling point of 100 degrees and change the phase of it from liquid to gas. The R here is actually the energy R gas constant, is the 8.314 version, joules per Kelvin per mole. And obviously our temperatures here would be in Kelvin for everything to properly cancel out. So if we look at this here, we have the vapor pressure of water at 25 degrees. So our T1 here would be 25 degrees. And our P1 here would be 23.8 torr. The heat of vaporization, which is delta H of vaporization, is 43.9 kilojoules per mole. What is the vaporization at our second temperature of 65 degrees Celsius? And again, we would be looking for, in this case, basically P2. So in this particular formula that we see here on this page, which again is our natural log, basically P1, P2 is equal to delta H of vaporization over R, or 1 over T2 minus 1 over T1 in that particular case, right? That's the version it has, I think, yep. So we do have to convert our temperatures into Kelvin. So we would do a plus 273 here, going to give us a 298 Kelvin. Here we'll do a plus 273. And that's going to get us here 65 plus 273, 338. In this particular case, you actually can leave the pressure values in torr. You don't necessarily have to convert it to atmospheres or anything like that, because as long as these are two in the same units, everything will cancel out correctly. So if we do that, I'm kind of putting it in here. We have the natural log of our P1, which is 23.8 over our P2 is equal to, this is also a really important thing when we think of R, which is 8.314 joules per Kelvin per mole. It's really important in this case, this part of it here. This is in joules. This guy's in kilojoules, which is a very common thing. So you do need to do a conversion. Otherwise, you're going to be off by a factor of 1,000 when you put those units into this equation. And it's this part right here where people screw up a lot on this one. It's that unit wise. Again, one is typically in kilojoules, one is in joules. So you got to do some type of conversion to get them into the same units. So for me, I'm going to convert the delta H of vaporization, and I'm just going to convert it by taking 43.9 and times it by 1,000. That's going to actually convert it into joules. And I'm going to then divide it by my R, which is in joules. So everything's good in terms of units. So again, really important, that part of it, so that the units do cancel out. We will then do, I'll get rid of that. So I got some room to write here. There we go. We'll do our temperatures here. So it's going to be 1 over T2, which was 338, minus 1 over T1, which was 298 Kelvin in this case. So I'm going to clean up pretty much this side here. So I'm going to clean up everything on this side. So we're going to take 1 divided by 338. It equals minus parentheses 1 divided by 298, close parentheses. And then times it by 43.9 times 1,000. And then divide it by 8.314. And if you do all that good stuff there, you'll have the natural log of 23.8 over P2 is equal to minus 2.0969. To get rid of the natural log, you actually on your calculator need to take the E button there. And that usually is found above the natural log button on your calculator. That's usually the button that you need there. So you're going to do that to both sides. And that will get me, when I do that on the left-hand side, the natural log just cancels out. And that gives me 23.8 divided by P2. On the right-hand side, 0.12283 and change. I'm going to multiply P2 to this side and then divide this guy back over to this side. So essentially, I will end up with P2 is equal to 23.8 divided by 0.12283. And I will end up with, thank goodness, the answer that's on the screen, 194 basically. And that would be torr in this particular case. Any questions on the math there? So again, that E button is typically found above the natural log button on your calculator. So what do we see here? We do see what we've been talking about, which is in this particular case, at 25 degrees Celsius, we have 23.8 in terms of the pressure. At 65 degrees Celsius, that is a higher temperature. That means that those gas molecules should have more energy, right? Should be able to move a little faster and be able to escape each other a little bit easier. You're going to get a greater number of the liquid molecules going into the gas phase. The result of that is we see a lot more vapor above the liquid, and we see the pressure above the liquid, or the vapor pressure, increase because of that increase in energy, basically in temperature. And again, that allows, as we also talked about with gas molecules, right, more temperature going to be moving a lot faster and be able to kind of break away. Any questions on that calculation there? So let's talk a little bit about some of the processes that we see with liquid. And one of the processes is boiling. And boiling is when a liquid is heated to a high temperature. What tends to happen is you start to get bubbles forming, as we know, waiting for all that stuff to boil during those experiments, right? Now, when you actually get something boiling, they're able to sort of escape the liquid phase. Basically, the vapor inside the bubbles are able to escape the liquid phase by making its way to the surface. Now, when you first put like a beaker of water up on the fire, you may actually see, for example, a bunch of little sort of bubbles, I guess, in a sense. And sometimes people think, oh, it's bubbling like right away. And it's not, obviously, because you just put the fire on it. What you're actually seeing is the change in temperature is going to make something like CO2 less soluble in the liquid part. And that's what all those like really quick, like bubble type things that you see when you first hit it with like the flame come out. It's obviously not boiling at that point because you can put your finger in there and it's obviously not very cold, or it's very cold at that point. When it is truly boiling, right, you are creating these bubbles that basically have vapor in there, enough vapor pressure to basically withstand the atmospheric pressure that's pushing down on it, right? And if the bubble can't handle that, before that, it will pop before it gets to the surface, right? Before it does that, because the vapor pressure inside is less than the outside. Once you hit sort of that equal vapor pressure or so, that's going to allow that bubble actually to make it to the surface. And obviously, when it does, it can pop and obviously allow it to go into the gas phase. We know that happens as well because as you leave, right, a water thing boiling, right? And it really starts to bubble and boil. Eventually, right, your water level starts dropping and dropping and dropping, right? Because all the boiling parts of it, those are the guys getting to the surface, popping, letting all that vapor coming off, along with just the steam coming off, which obviously is the vapor of water coming off as you're heating it up. So eventually you're losing that volume of liquid part that you have in there as you are boiling it. And again, that's why when we put lid on a container without heating it, uh, you will see that sort of change in liquid level. That's also why we don't heat closed containers, right? Because as you heat a closed container, you are creating a bunch of vapor pressure above the liquid, right? And that vapor pressure above the liquid will eventually have nowhere to go and pop goes off your container, right? If you continue to heat it. And again, that's why obviously we typically don't heat a closed container like that. As I mentioned before, it will continue to boil and it will boil and those bubbles will form when the pressure inside the bubble again is equal to or greater than the atmospheric pressure, and that will allow it to actually get to that boiling point. The temperature at which something boils is dependent on both temperature and pressure. So depending on your temperature pressure conditions, although we think of boiling for water, for example, as being 100, you could boil water at a much lower temperature, for example, or even perhaps a higher temperature, depending on the temperature pressure combination at which you're at, right? So if you go to some place that's a really high altitude, it will boil perhaps water at a different temperature than you are here closer, say, to sea level, because of the difference in the pressure. Now, one way you could kind of increase the boiling point is, for example, something like you see in a pressure cooker. The lid keeps really high pressure, and then what that does is it increases the boiling point. So instead of say it boiling at 100 degrees Celsius under this really tight pressure, it holds that vapor pressure in, and the resulting part is it's going to take a lot more pressure and energy for those gas molecules to escape. So it's going to take a lot higher of a pressure for those guys to gain, higher than, say, atmospheric pressure to get out there. The result of that is you need a lot more temperature to get those guys enough energy to basically escape to the liquid part of it. Now, as odd as it may sound, boiling is a cooling process. And boiling is a cooling process because as quickly as you heat it from the bottom, it is actually cooling from the top. That is why sometimes people, when they take a thermometer and they put it into a beaker in the laboratory and they worry because the thermometer only goes up to like 100 or 2 maybe degrees Celsius. So they're concerned that, isn't my thermometer just going to break because it's just going to keep going as you're boiling? And it will not. So when it hits something like the boiling point, it basically will maintain that temperature because, again, just as quickly as you heat at the bottom, is basically cooling at the top. The result of that is as you heat it, these guys are gaining energy, but then you're losing that energy out the top in the form of them being in the higher energy gas or steam that's coming off at the top of it. So the process of molecules converting back to a liquid is going from a liquid to a gas is evaporation and condensation. So those processes as we go from liquid to gas or gas back to liquid, that is evaporation. And going from gas back to liquid is condensation. And in terms of energy, as we might have touched upon earlier, it is endothermic. Energy is absorbed as you go from liquid to gas, right? In order to get those liquid molecules to go into the gas phase, you have to put energy in there so they gain enough energy, they can escape the liquid phase and get into the gas phase. Opposite way is exothermic. Energy is released and The result of that is when you have gas molecules flying around really, really fast, they release their energy and they're flying around, they no longer have enough energy to escape each other when they kind of collide, and they sort of collide and clump and drop into the liquid phase. And again, as you obviously continue to remove the energy, they will then tighten up into the solid phase, right? As you get rid of that energy. So condensation again is an exothermic process. Evaporation is a endothermic process. At the surface of a liquid, there is a constant exchange between the two. So as I mentioned before, at the surface of any liquid, even though you might not be able to see it per se, you have that exchange continuously sort of happening. You have faster moving, more energized sort of liquid molecules that have enough energy to escape the surface of the liquid. You also have flying around above it, slower moving guys that basically will fall back into the liquid as they lose energy. So as liquid molecules escape the liquid phase, they take a lot of their kinetic energy with them, and that lowers the kinetic energy of the liquid water, and it's being cooled. So if you think about it, as you're boiling, you get all these really fast moving molecules that are now leaving the liquid. So the liquid is actually losing all that energy as it goes out the top of the boiling part. As a result of it, though, the molecules that basically have escaped, they have lost a lot of kinetic energy that was needed to escape. So when they actually end up in the air, they're actually moving slower than air molecules because they needed a lot of energy to escape the liquid. And they kind of after the end, they don't have as much energy as they did as they were escaping. The result of that is the air actually is cooled along with the liquid. And again, this is why sometimes boiling is considered a cooling process because of that. As the water cools and evaporation rate increases, um, we will start to see that evaporation occurring. It is also what is used, for example, to say cool yourself down, right? That is why you sweat. You sweat because when you sweat and you have water on your skin, that water will then want to evaporate, basically. The only way that water can evaporate is it's going to use the heat from your skin to do so, right? And that what cools you down because your body is now releasing the energy from your body to evaporate off the liquid of your sweats, right? And now you will cool down. That is also why you feel really cold when you get out of the pool, right? Or the shower where you have a lot of water on your skin. And when you have a lot of water in your skin, the rate of evaporation that's going to happen is pretty high. And again, all the energy is coming from you, right? And that's what's going to provide the evaporation. And that's why you start to feel really, really cold in that type of process. So evaporation is a cooling process. Again, we use obviously sweat so we don't overheat. And again, that's also why when you take, again, like say a shower or get out of the pool, you have a lot of water on your skin, there's a very high rate of evaporation, and basically your body's losing energy basically as a result of that, right? At the surface, when we have condensation and evaporation occurring, condensation occurs when slower moving water vapor molecules stick to the surface of the liquid, and they sort of reintegrate into the liquid phase. That is also why condensation is considered a warming process and why you feel warm when you take a hot shower, probably. When you take a hot shower, you create a lot of steam, right? A lot of steam when it hits, for example, you can see this physically usually if you have a mirror or something in your shower or in your bathroom, the mirror gets really wet, right? If you take like a hot shower, right? You have a lot of condensation on the mirror. You can wipe it away, right? And it's like watery. And that is because all that steam that you're creating during the shower is going through condensation, which is an exothermic process. So opposite when you're wet, per se, and you have no sort of hot sort of situation happening, when that process of that steam goes through condensation, it's going to release all that energy to you, which is your body, right? You're going to pick up all that energy that's being released by all the water going through condensation in a really hot shower, right? When you shut off the water, obviously at that point, you're now just wet sitting in a room where it's not a lot of steam. And now you go through the process, right, of evaporation. You start to feel really cold after your shower, but you feel okay during the shower because there's a lot of steam, a lot of condensation occurring, releasing energy into the room that you're picking up, and that's why you kind of feel warm when you're taking sort of a shower that's, say, warm in that situation. Um, Now, as I mentioned before, the molar heat evaporation and condensation, evaporation and condensation is known as the heat of vaporization. Since we don't talk too much about it, as I mentioned before, that is the same numbers I gave earlier. It's like 2260 joules per gram. This is for water and kilojoules per mole. The only difference is when we talk about the delta H of vaporization is as we go from liquid to gas and gas back to liquid, it would be a positive, for example, 2260 joules per gram, which is the delta H of vaporization for water. And it would be a negative 2260 joules per gram as you go from gas to liquid. It's the same amount of energy required to go either way. And again, we're talking about the point, for example, for water at 100 degrees Celsius, exactly just that flat line of temperature doesn't change, but it goes from liquid to gas or gas to liquid. The energy just to do that, it again is the same value, just whether or not it's going to be released or absorbed, depending if it's endothermic or exothermic. So as I was mentioning before there, again, that's why, again, as we talked about in the shower, you do feel warm because of the high rate of condensation that's happening in the room. And then obviously at the end of the shower, you actually have a higher rate of evaporation happening, which is why you feel cold. That's also how those like packs work. Like you break it and it either like warms your hands or cools your hands, right? And when you do that, it creates either an endothermic or exothermic reaction inside whatever the bag is that you're going to use for that. Again, if it makes you feel cold, it will create a process where it's going to basically take the heat from your body into the reaction. So it'll be an endothermic reaction happening that will suck the energy out of your body. And if you feel hot, it will be an exothermic reaction that's happening in the hot pad bag or whatever it may be, because it's going to release all that energy into your system or your skin, and then it will feel hot in that situation. Now, freezing and melting is also another important sort of transition that occurs, and that's really the transition between solid and liquid and solid. Once again, it is an endothermic process going from solid to liquid. It's an exothermic process going from liquid back to solid in that particular case. The process of melting occurs as we go from solid to liquid. Freezing is our liquid back to solid. It again does occur at the exact same temperature for water that's 0 degrees Celsius. And just like we saw with liquid to gas and gas to liquid, there is a delta H of fusion is referred to. And that's the energy required to do that change, go from solid to liquid or liquid back to solid at the normal melting point, freezing point temperature. Again, for water, that would be 0 degrees Celsius is basically where that occurs. By the way, for something like water, the delta H of fusion is about 335 joules per gram. And as we talked about a second ago, the delta H of vaporization is like 2260 joules per gram for water. And you can see just from the difference in the numbers, it takes a lot more energy to do the transition of going from liquid to gas versus the transition of going from solid to liquid. The transition going from solid to liquid is only like 335 joules. To go from liquid to gas, the transition is 2260. And that's because as you go from liquid to gas, you need to get everybody completely broken apart from one another to fly around and go into the gas phase, as opposed to as you do sort of this transition, as we go from solid, where everybody's packed in pretty tight to each other, to liquid, where they are still relatively packed in tight to one another. It doesn't take as much energy to kind of get everybody moving because they're still quietly associated to each other, as opposed to here when we go from liquid to gas, everybody's kind of close to each other to everybody is kind of way far from each other and flying around. So again, it takes a lot more energy to get everybody separated from one another. Now, to get water at 0 degrees to form ice, we do have to release energy. And it does bring up an interesting sort of aspect of water that we talked about as well. Because of the hydrogen bonding, actually, again, in ice, which is here, it creates a lot more empty space, right, between the water molecules. In a liquid state of water, they can actually get much, much closer to each other, but without that excess amount of energy that you have here, that allows them to kind of move a little bit closer to each other. As you continue to release the energy in ice, again, they can't have enough energy to get that close to one another. That affects one of the interesting properties of ice or water that we talked about, which is its density. Because in the solid phase and they don't have enough energy to really kind of lock themselves close to one another, that increases the overall volume of ice. And the result of that is the density goes down. That is, as we talked about, the reason why ice is less dense than liquid water, which is an unusual sort of characteristic of a substance. Usually in the solid phase is much, much more dense than in the liquid phase. But again, the combination of the really strong hydrogen bonding and the lack of energy doesn't allow those water molecules to get really, really close to each other in the solid phase as they can in the liquid phase where they have a little bit more energy. So they're able to kind of move in a little bit closer to one another. Any questions on that there? Now, the last sort of transitions is sublimation and deposition, and that is the transition of solid directly to gas. We skip the whole liquid process and gas back to solid, skipping the liquid process. Again, this is sublimation happening. This is deposition. And again, in terms of energy, this is still endothermic this way and exothermic heading in that direction. Sublimation is the process where basically it sort of gains enough energy to basically just leapfrog over the liquid phase. So dry ice is an example of that. Dry ice, which is really carbon dioxide, goes directly from the solid phase to the gas phase. The skip is the liquid phase under normal conditions altogether. Deposition is the reverse process, is the process where we do go from gas directly to solid, also skipping the liquid phase. I guess maybe they still sell CDs or DVDs somewhere, I suppose. But if you look at a CD, DVD, it's really shiny. That's the process they use, for example, to get the metals on top of them to make it really shiny. They do deposition sort of process. Usually, the amount of energy to do sublimation or deposition is basically the total energy to do both, obviously, fusion and heat of fusion and heat of vaporization basically together. That takes you through the entire process. Now, as I talked about, the energy to change states is required. And again, the heat of fusion is what we use as we go from solid to liquid or liquid back to solid. Again, not changing the temperature, and our heat of fusion, which is our delta H of vaporization, going from liquid to gas and gas back to liquid. Something, again, we don't talk about in this class, which is a lot about energy, but maybe it did in the previous class. But when we talk about something like specific heat, which is Q is equal to ms delta T. That's the equation, for example, or that version of the equation. Q is equal to C delta T, or whichever version you use there in your class. Q is equal to MSH delta T. This is the heat or energy. It's typically in joules or calories. M is mass, which is typically in grams. S is the specific heat capacity. These are typically have units, like the 3 units of joules per gram per degree Celsius are calories per gram per degree Celsius. For example, the specific heat of liquid water is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. And delta T is the change in temperature, actually. final temperature minus initial temperature. One of the few things in chemistry that you actually don't convert to Kelvin a lot of times. You leave it in Celsius, and that's because our specific heat capacities are typically in Celsius as well. But we're not getting into this equation too deeply, but that's the equation that you would use if you are in the same phase, but you change the temperature and you want to know how much energy is required to do that. So for example, you would use this for the same phase, but different temperatures to figure out how much energy. So if you want to know if you had water, liquid water at 25 degrees Celsius, and you wanted to take it to 85 degrees Celsius, liquid water, it is liquid water all the way through that process. And that would be the equation that you would use, obviously, to plug in and solve for how much energy is required to do that. So a lot of times, the reason I bring that up is a lot of times if you're doing some type of energy calculations, that specific heat equation that you might have seen previously, along with the heat of fusion and heat of vaporization are used together to figure out a process of as you're sort of changing phases with a substance, how much energy is required to do so. And that's what you see here. So for example, this is a heating and cooling curve, is heating going from down here, that is solid basically. This is liquid water, and that is obviously steam, which is gas. So as you go from solid to liquid to gas in this direction, it is a heating curve. But as you go in the opposite direction from gas to liquid to solid, it is a cooling curve. Again, endothermic in this direction, exothermic in that direction. So when we look at this graph, what we see here, right here, is where our heat of fusion would be. Our delta H of fusion would be used at that transition. It is a flat line at exactly the normal melting point or freezing point of something like water, which is 0 degrees Celsius. A flat line means that the temperature is not changing, but the phase is in this case, and that's where you would use the heat of fusion. The heat of vaporization would happen here at this flat line, and that is the delta H of vaporization, and that's at exactly 100 degrees Celsius, which is again for water, the normal boiling point. As you can see, we're not changing temperature, we're just strictly taking it from one phase to the next. This is why evaporation condensation happens at the same temperature, as it is not changing. And same thing with here, melting and freezing happen at the same temperature. When you're exactly at those points, these guys are said to be in equilibrium with each other, which means you basically have both phases happening at once. So when you talk about water at 0 degrees Celsius, at exactly 0 degrees Celsius, you have like ice crystals. So you got some solid there, you got some liquid sort of happening. It's not until you get above 0 degrees that you fully transition into the liquid phase, not until you get below 0 degrees that you transition into the solid phase. Same thing up here at the normal boiling point, like 100 degrees. Exactly that, you have a little bit of liquid and sort of gas happening at the same time, not until you get above 100 degrees for the case of water that you actually do sort of go into fully gas, and a little below, obviously 100 degrees, you would be in liquid water at that point. So this is curve that you probably will use next semester when they talk about energy, but you'll use that specific heat equation and also the heat of fusion and heat of vaporization together. Pretty much anywhere you look on this curve where it is going upwards, those are all spots where the phase stays the same all the way through, but the temperature changes. So anywhere where you look at this curve, it kind of goes upwards. Those are all spots where you would use that specific heat equation. Anywhere where it's sort of flatlined is a phase change where you would use delta H of vaporization or delta H of fusion. Any question on that there? So let's talk a little bit about phases and phase diagrams and sort of what we will look at them. A phase diagram is actually a diagram that shows the 3 phases of matter and the 6 interconversions between them. You may be wondering, what is the 6 interconversions between them? Well, we have solid, we have liquid, and we have gas. Those are the 3 phases of matter. We have solid to liquid, which is we've been talking about is melting. liquid to solid, which is freezing, liquid to gas, which is evaporation or vaporization, gas to liquid, which is condensation, solid directly to gas is sublimation. And as we talked about, gas directly to the solid is deposition. So by my count, that is 6 interconversions there. So 1, 2, 3, 4, 5, and 6. Yeah, so there's the 6 interconversions is what we're talking about here. So when we look at a phase diagram, there's a couple of important sort of points on it. One point is what is referred to as the triple point. And basically, when you look at a phase diagram, there's two things basically shown. There's temperature and pressure, basically what is shown on a phase diagram. And the triple point is the temperature pressure combination where if you hit that combination of temperature and pressure, you will have all three phases occurring at once. So the substance will be at the same time in the liquid, gas, and solid phase based on that pressure temperature condensation combination. Water, as we will see, has an unusual sort of negative sloping line, and that accounts for why ice is less dense than liquid water. Now, a couple of other important parts when we look at this diagram. One is the critical temperature. And the critical temperature is the temperature where if you go above that temperature, there is no distinction between basically liquid and vapor. It's sort of the temperature where they sort of blend together. The substance has some properties that are much like a gas and also some that are like a liquid as well. So kind of a blending area. You also will usually have a critical pressure that goes with that. And that's sometimes just referred to as the critical point sometimes. And that's like the temperature pressure combination where if you go above that little point on the graph and that temperature and pressure combination, you're going to really have a liquid where are a solution that can behave more like a liquid and a gas together. And that is really what is sometimes referred to as a supercritical fluid. It is one where you're above that kind of critical point, and that is where the substance has the density of a liquid, but it will actually flow like a gas. So it has sort of the properties like a liquid, but will actually flow and move more like a gas. So let's take a look at one here. This is a generic sort of phase diagram. And the general parts that you do need to know, obviously, is what's on here. So solid is typically to the left here. As you can see there, liquid phase and the gas phase is usually to the right when you look at this. This is the pressure and temperature combination. Right here, where all those lines come together, is the pressure and temperature combination where all three phases, solid, liquid, and gas, basically come together. This is the melting point and freezing point line right here. So this is your normal melting point and freezing point. That is the temperature pressure combination where you'll have that transition. So as you transition across that line, you're going from solid to liquid, which is melting, and going the opposite way, liquid to solid, which is freezing. This is the boiling point sort of line heading in this direction. And again, as you cross that line, you're either going through evaporation as you go from liquid to gas, or condensation as you go from gas back to liquid in that particular point. That is our triple point, our critical point right here. That's our critical point. That is the critical temperature and pressure combination where if you go above it, you'll have that supercritical fluid. And as you can see, that is liquid kind of bleeding into the gas phase over here. And there's kind of no real distinction between the two. They will have properties of each. Down here, if we go below our triple point, this is our solid directly into gas. So that is the transition between solid directly to gas. We at no point went to liquid, which is up here. So we do not cross liquid at any point there. And that is our sublimation occurring as we cross that line and our deposition as we go back the other way. Again, not passing through the liquid phase. By the way, normal standard pressure is 1 atmosphere. Yeah, is one standard pressure. So if you find the 1 atmosphere line on a graph like this and just draw a line straight across, that would be your normal melting and freezing point right there, where we cross the transition between solid and liquid, and where it crosses over here, right, would be your normal boiling point for that particular substance. You then could draw a line straight down and figure out the temperature at which that occurs for that particular substance, what the normal boiling point and melting point would be. So typically 1 atmosphere is the sort of point where if you're looking for the normal boiling point, our melting point would be just kind of draw a line, and where it crosses those guys, you can then go down and figure out the temperature at which all that occurs. For something like water, that would obviously be somewhere hopefully near 100 degrees Celsius. And for something like water, that would be near 0 degrees Celsius if we went down. And this was water's sort of diagram. So you do need to know a phase diagram where solid, liquid, and gas is located. You need to know where the triple point is located, where the critical point, temperature and pressure is located, and where the transitions of melting, freezing, evaporation, condensation, sublimation, and deposition occur. Any questions on any of that there? So we look at the phase diagram, for example, for carbon dioxide, as we see here. That is why when we think about carbon dioxide, which is dry ice, as we talk about under normal conditions, it goes through sublimation. Why is that? Well, here is 1 atmosphere, which means if I draw a line straight across and normal 25 degrees is right about there, it passes through only solid and gas, right? It does not go through liquid. So that is why under normal conditions, when you have something like dry ice, it will actually go directly from solid to gas. It doesn't pass through the liquid. How much pressure would I need to get it into the liquid phase? Oh, it has to beef it up above at least 5.1, right? And then move it across, right? And have it at a temperature somewhere in that region that you would need. So you would need about 5 times the normal pressure to force dry ice into the liquid phase, and also, get it at a temperature would be probably really, really cold. So again, that's why when we look at something like dry ice, it does not normally find itself in the liquid phase under normal conditions, because again, normally we're about 1 atmosphere-ish in that ballpark. So that is not enough pressure to force it into sort of the liquid phase. Any questions on that there? All right, so for each of these conditions, using this phase diagram that we see down here, what phases would CO2 be in? So take a moment, look at the diagram, and figure out, based on the temperature pressure difference there, what phases we would expect CO2 to be in, and obviously gas would be here. Okay, so let's take a look and see. So we're going to use this phase diagram here and really just kind of figure out where we're going to end up. So we have 20 degrees Celsius and 72.9. So obviously 72.9 atmospheres is this dotted line up on top. And 20 degrees would put us, I don't know, that's 31. So I guess we would be somewhere like in that area, I would imagine. And that obviously is in the liquid phase, right? So we would expect CO2 to be in liquid phase. So that's quite a combination. At 20 degrees Celsius, you need about 72.9 atmospheres to get it into the liquid phase. Normal temperature for us is, 25 degrees Celsius or so. So that's an incredible amount of pressure to get that carbon dioxide into the liquid phase. At minus 56.7, which would be this line right here, and 5.1 atmospheres right about there. That is the point where all 3 phases come in contact with each other. That is the triple point. So that looks like we should have solid, liquid, and gas basically happening at that particular point. Any questions on that one there? At 10 degrees Celsius, I don't know, maybe in this ballpark. And 1 atmosphere, which is about here coming across. So, probably somewhere in that ballpark is where we should end. And that looks like that would put us right there in the gas phase at that point. At minus 0.5 degrees Celsius and 1 atmosphere, which is right about there. That's going to put us in which phase? It's actually going to put us in solid and gas. It is right on the line, right? So that's the transition line between the two phases, which means you would actually have both phases happening right at that point, right? Again, it's kind of like not until you get over the line one way or the other that you fully would transition into the other part. So again, if you sort of hit one of the melting point lines, boiling point lines, whatever it may be, you'll have both phases sort of occurring. Lastly here, 50 degrees Celsius, which is past over here, I think, and 80 atmospheres, which is up here. That is going to give us a supercritical fluid, right? And that's the part where they kind of just flows into each other, the liquid into the gas phase. It is past the, right there would be your critical point, right? That's where your critical temperature, critical pressure would be. And this is above it and past it, which means you have basically that supercritical fluid. Any questions on how to read a phase diagram there? Okay. So like I said, you do need to know where all those parts are on a phase diagram. You need to be able to use a phase diagram that's given to you to figure out those things, solid, liquid, gas, what phases and stuff you're in. Any questions on about there? All right, so let's talk a little bit about water here. Water, it's 3/4 of the globe. It's obviously made up of water. Um, it has the ability to hydrogen bond because of the OH bond there, which is a hydrogen directly attached to an oxygen, and it's a polar molecule. As we talked about, the density of ice is a lot less than liquid water. And again, that is why ice will float, as we talked about, again, because of the hydrogen bonding and the lack of energy in the solid phase. Again, they just can't get themselves super close to one another. And that's a very unusual sort of characteristic of a substance, as we talked about before. Typically in that solid state, you're going to be a lot more dense. And again, it's that hydrogen bonding, that intermolecular force that accounts for that, along with the lower in energy. Now, as water gets into the solid phase, it does expand. And maybe you've done this before. It's very common, right? You throw something in the freezer to cool it down and forget you put it in there, like a water bottle or a can of soda or something like that, right? You come back later and all of a sudden, right, your can of soda is wobbly because the bottom of it is like expanding out. And that's because obviously as you freeze, say your soda or water or whatever it may be, not so much in water, but most lots like an aluminum can, it happens a lot. The water obviously expands, right? And obviously it only has so much room in there, but as it expands, you'll see the bottom of the soda can kind of expand out with it. And again, it takes up a lot more space in that solid form in terms of its volume than it does in the liquid form. Now, this is also, though, a really good thing, for example, in terms of sea life, if you will, in terms of how water freezes, right? So water actually freezes from the top down, which is really good, because if not, then we would have a lot of not so happy fish, I suppose, right? There would all be ice cubes and stuff like that. Um, or could you go ice fishing, I suppose, if it froze the other way around? And that is because as water sort of freezes, it is most dense basically at 4 degrees Celsius. So as water starts to freeze, the kind of warmer water actually goes to the bottom because it's more dense. The colder water or cooler water will actually go to the top. And that's at the top there where it starts to freeze, right? Which is why they tell you to be careful if you step on like a lake or something that's just as frozen. It's not very thick, probably, right? Because it's just a small layer of ice on top and you could fall through, right? But what it does is as it starts to, and it'll be obviously very cold water underneath it, but as it starts to freeze, it actually will start to insulate the water that's underneath that sort of ice and actually will prevent it from freezing, which is really good, as I mentioned before, because you have fishes moving around and they can still obviously swim around in the liquid water just a little bit colder. If it was the other way around, that would probably be disastrous, right? because it would freeze from the bottom up, and anything obviously there would not be able to probably survive obviously in the frozen ice. So that's good that it doesn't do that. Again, the warmer, I guess 4 degrees Celsius, which is not super warm, but the warmer water than the ice at 0 degrees Celsius, which makes that insulated layer. And that's really good for a guy like my friend here, Melvin, right? The fish, right? So that will probably be on the exam, I imagine, on Monday, his name. So that's Melvin. Even though he does look like he's in an ice cube, he's really not. It's just an old clip art. So it wasn't so good. But he's not really floating around in an ice cube. But he's swimming again here. The warmer kind of 4 degrees water will go to the bottom. The colder kind of 0 degrees water will go to the top. Again, creating this ice up on top, freezing the top part of the water, but insulating the bottom from sort of freezing as well. All right, any questions on that? I think this is probably a good place to lay it up here for today.